Hello guys, good afternoon. So after a long time, we are going to cover another series of the video. I'll be live coding how to use the Fifo, Xilinx Fifo. Okay, so I'm just going to take you through that IP code, how to use that IP code. Okay, let me show you guys. Okay, so to use the IP core, first of all, we need to know why do we use the IP core. FIFO, why do we use, right? So you have to just search FIFO generator in the IP catalog. You have to go on this and you have to search FIFO generator, right? So you have to select this IP core. I have already generated to make the short video. Okay, guys. So I'm just going to show you how to configure this for the different. So generally Xilinx IP code comes into the native interface, XI memory map interface, and XI stream interface. So basically, FIFO is the first in, first output kind of buffer. You can store the data, you can write the data in the one side of the FIFO as like pipe. You are pushing the data in the one side of the pipe and you are reading the data from the another side of the pipe. So mostly use the FIFO in while we are crossing the clock domain, right? If let's suppose if our transmitting clock domain is transmitting the data at a rate of 100 megas, but your receiving clock domain or receiving module, your component is not working at the 100 megas. It might be working at 10 megas, 20 megas, or less than that as well. In that case, we use the FIFO. And another use also FIFO, basically in the FIFO and the program. That's a difference. Basically, FIFO is used to write the data one times and read the data. If we read the data which has been already written to the FIFO, if you read it, it will vanish. You can read only one times. But in case of the program or in case of ROM, you store the data permanently. You can read anytime you want to read, right? But in case of Bible, if you read the data, it will vacate the space. Okay, so there are the different types of Bible. As in the first case, native interface. Native interface, you can see there are so many. FIFO implementation. I really want to implement the FIFO by common clock. As I already said you that you can have the multiple clocks. Like you can you can you can generate the FIFO with the block RAM, which is the small storage inside the FPG that is 18 kilobits of memory, or it can be the 36 kilobits of the memory in case of Xilinx block RAM, and you can use the distributed block RAM. Distributed block RAM, this block RAM is used by the LUTs, which is already inside the FPGA. So if you implement your logic in the distributed block RAM, it will be consuming lots of space of the FPGA. So better to use the block RAM, and there is a clocks, right, for the read clock and the people write and people read. Here you can see as a million clock. This is the synchronous people, right? If you want to make it asynchronous, you can go with the independent clock ramps, right? So as I said already, if you're transmitting is if one component transmitter is working at the 100 megahertz, but the receiver is not working at the 100 megahertz. It might be working less than 100 megahertz, 50 megahertz. Like on that case, we use the independent clocks. Okay, guys. So here you can say right clock and the read clock. So time being I'm using the common clocks. Okay. So synchronize stay now. You can see non-symmetric aspect ratio as well. You can see that means non-symmetric means the read and write both can be the reference. Here, if I am reading that the eight, if I am reading the 8 bits of the data, but if I yeah, I can read the data 32 bits of the data as well. Write depth. This means how many depth there will be the depth of the memory. That is 1024. You can select any number from the 16, 16, 32, 64 up to you go to the maximum number. Okay, so for now we are using for now we are using only the depth of let's suppose we are writing to 16. Okay guys, so the depth of our memory will be only 16, right? Also you can use if you can make it reset high or reset enable or disable, you can do this. And also here you can select the pipeline stages output register. If you select that here, after how many clock cycle you want the output, right? Here you can read latency. That means after 2 clock cycle you will be getting an output. And the register will be the embedded register. What register you want to make the pipeline? That means it can increase the frequency as well. So for time being, we're not going to make it as a pipeline. Okay. So then we'll be getting the output to the next rising edge of the clock, the read bus. So here as well, there's a status flag, almost full and almost empty flag. Right, you can see here, almost full. If you're writing to the Fifo, then almost full flag. That means if there is one space remaining, then this flag will go high. Almost empty. If there is if there is only one space empty to write, empty to read, in that case. Empty flag will be high. There is only one data is written, right? In that case, read. In that case, almost empty. If there is, if there is only one data is remaining to read, on that case, the almost empty flag will go high. Okay, guys. So, time being, we're not going to use this flag as well. Also, right actor is valid flag you can generate, and another programmable flags you can generate out here. Here the different flag you can generate as well. Here you can see the single programmable full threshold constant. That means if you do this full programmable full, and you can set the threshold. You have the depth of 16, and if you can set here the 14 right, 14 clock cycle right has been done. On that case, this flag will go high. Full threshold negative value you can set, right guys? So you can set you can go with and set it to the multiple threshold value as you like. You can set that value. So for time being, we're not going to use, we are just going for the simple no programmable threshold. Okay. So data count as well, how many data bits has been written, how many addresses has been already returned to the FIFO. You can make it counters, data count, and you can use it as well for the debugging purpose. You can use that. Okay. Because we have only 16 addresses we had selected, so here is counter is 4, but if you increase that addresses 32, then it value will go to 5, right? You can see as 4 down to 0, that is 5. And as I is for timing, I'm just going to disable it. And as I said that, I can go to the block summary here, right? Data width and the read data width, right depth, we have made it 32 addresses. Okay, guys, so We are using the single clock read latency, that is 1 clock cycle. This is going to use the block RAM and we have the model clock we are using synchronous fiber. Okay guys, so we have already generated, and one more thing I'm going to discuss about XI memory map fiber. In this XI memory map, if you are going to write the data, you need to provide the address as well where you want to write the data, write length, and when to read the data, you need to provide the read addresses like that. There are so many. This is the XI combination, and right XI for XI string. Five, there is no read and write address. Right, guys, you want to provide the valid and the ready signal. Valid and the ready signal for this. Okay. So this about the FIFO and how to use this. So we are going to test it. We are going to write code. Okay, guys. So just you can click OK, and you will be generating. It will be generating the. So after clicking OK, you will be generating this file. Okay, if you can extract the hierarchy as well. Okay, guys. So I'm going to show you every Xilinx, because Xilinx IP core, Xilinx will not provide you the full Verilog source code. They will provide only .tcp file, which Xilinx but will not understand, right? So these files are for the simulation for the VSTL and Verilog. This file will be going to involve. Okay, guys. Okay, so now I'm going to discuss about the this file is and used for the netlist generation. Okay, so for the Verilog and the VSTL, this file will be using for the generation of the netlist. Okay, guys, so so here you can see, and beside the Fifo generator.psu for the Verilog templates and VU for the PHU for the VSTL template and VU for the Verilog template. That means component, right? So we are going to use the VSTL template. So we are going to test with VSTL. Okay, so I'll be demonstrating it how to simulate and how to analyze the behavior of the fiber. Okay, so I'm going to create the top file. Okay, so here you can use the Xilinx.exe is the extension for IP. Xilinx core interface. Okay, guys, so I'm going to create the. I'm going to add the source. I'm going to make as a top file. Fifo test. I'm going to give it name as Fifo test pens. Or I can give as Fifo test. Okay. So I'm just going to miss it. Okay, guys, after creating the top file, we'll be setting that our generators. Okay, let us wait 1 2 minutes, and okay, now it is created. So I'll be giving, I'll be writing some port list first and comment it. So now I'm going for the FIFO. We require the clock signals. Okay, STD logic, right? Reset STD and we'll be writing the data. So we are writing I data, right? I data. Because we're writing the 8 bit of the data, so we are going to take it as vector 7 down to 0. Down to 0, and we'll be reading the data as our data. Vector 7 down to 0. And another what will be analyzing that full and empty, right? Okay. Okay, guys. So these are the signals we applied for the Fifo, and we'll be calling our component. Okay, we'll be calling our component. You can uncomment this library Unison by component.all. You can just use it as a component 5% later. Okay, there are two more signals. We just forget it. Write enable and the read enable signals. Okay, so we need to give it. Okay, right. Enable stereo logic. Okay, guys. So we're done with the component calling. Now we are going to port map. Fifo instance. Okay, guys. So I'm just going to copy and paste it. Just got it. And here you can write port map. Okay, guys. So just delete it. Now we are going to assign this clock. Reset. Reset is going to put map over here. Okay, guys. So just delete it. You can just map it. Okay, guys. Will be connected with the data. Right enable will be going to enable signal. Read enable will be connected enable. Layout will be connected with the home data, right? Data and the source. Signal will be connected with the an entity will be connecting with. Okay, guys, we are done with the instantiation. We just need to edit it. Okay. Anything is remaining, then you can check it. Okay. I guess everything is fine now. Okay, so time being, I'm going to save it. Okay, guys. So, okay. Now I'm going to cover it on the first way so that you will not get bored. You will be say now. After a couple of minutes, you will be seeing that this Fifo generator.xi will be coming down to the Fifo test. Will be the top model. Yes, you can see here. Below this, there is a 5%. Okay, so we are going to simulation. Now we are going to set it as top. We have to set it as a top file, and we are going to generate. We are going to simulate it. Okay, so it has been set off. Now we are going to variable simulation. We'll be analyzing all those. We'll be covering all the we'll be covering MPT and the full facts as well, and writing and editing the data from the right. Okay, finally simulation window has appeared now. Okay guys, so I'm going to create here partition for the FIFO. Okay, so I'm going to write it as FIFO. FIFO signal. So this is a divider and delete it using the okay FIFO signals. Now I'm going to add all the signals of the FIFO. Add to waveform. Now all the FIFO signal has been added over here. Now we are going to analyze it. Okay, so first of all, I'm going to give yes. I'm going to first clock 0, 1, and let's suppose we are using the 10 nanosecond. Clock period, clock of 100 megahertz we are using, right? So I'm going to make the reshape signal actually high, light enable is low, read enable is also I want to make it low. I'm going to let's try around for 10 clock cycles. 1 clock cycles. Okay. Let's run for 1 clock cycles. Now let's write some data to the people. Let's write 1. We're writing the data to 1. We have put the data 1 to the right bus. Right. So the data right. And this will be the data which will be coming from the flight. These are the data and these are the signals when we want to write and read the data. Okay. Now, okay. So timing, now I'm going to make it a reset as low. No, let's write for let's make for the right enable first. Right enable. We have made the right enable is synced over here, as you can see here. But the data will not be written yet since reset signal is high. We are going to make it as a 0. Yes. I just made it the reset signal low and we are going to write the input data. I'm going to write the input data as well. The data is full. That way I have to write the data. Okay. And I'm going to make it as low, right enable. And I'm going to read the data. As you can see here, empty because we have not read any data. Yes. Okay. Okay, guys. So as you can see here, we have just written the data 0, 1, 2, 3, 4. 4 data we have written and still, uh, okay. So we have not read any data yet from the people, and we are just going to read the data. Let the reading signal high. Okay, and here you can see the full is low, still low because there are 32 spaces. If you write 32 space, then it will become high. Let me show you if I make it as label. Okay, and I'm going to write. We have already written to 4 places. That means so there's still 28 places remaining. That means we need to run to 80 clock cycles. Okay, we are going to run it 300 clock cycles. Then we will be saying that the full signal, full flag will be going to high. Let me highlight the signals. Maybe that's great. Okay, so full flag. Okay, that to have made it. Right. Let's jump into here. So guys, now we are going to, yes, here is read enable. I have made the read enable high, right? Made the read enable high, and you can see the first. Oh, because this 01 has not been written over here because the reset signal was high. We have made the reset signal low over here. That's why you can see here 02. We are reading the data in the read bus. We have write the data into 01, 02, 03, 04, but while reading, right, we have write only after the data will be returned to the file only to the reset signal is low. That's why here, up, here in the read bus, you can see in this bus as well. In the read bus, we are getting the data to 02, 03, 04, all the way right 04. Okay, so this is the way we write the data and we read the data from the file. Okay, guys. Now let me show you. This I have made the file as 1024 already. I just forgot that 1024 depth. So for this, I will paste 10240. That clock cycle will be requiring to see the full, right? Okay, so I'm going to run this for this many clock cycles, and I'm waiting for that. I can see here how many clock cycles is. Okay, first of all, we need to make it as read enable because we are reading. That's why it is not going to full. We need to make it as a low, guys. Analyze that. Okay. We are going to run some clock cycles. Now rate enable is low, write enable is high. Let's suppose we are writing the data and the data is 0. That's why we are writing and we are going to run. Cycles. Now you can see we have written all the way to the 1024. 1024 of the file. So wherever it has reached that depth, it will full. We have to return all the way to the memory. Now we are going to make it as a low to analyze that all the bit which we have written already to the file. Okay, guys, so going to make it as a read enable high, and we are going to read, and this flag will be going to high after the 1024 bit is read. Okay, so here you can see. Okay, guys, so example modes. In petty, we have read all the data. In the read bus, you can see here as a file. Okay, it was full because we had already write on the data and we read the data 0. Okay, now I'm going to show you another example that asynchronous asymmetric fiber. We can use that asymmetric fiber. Okay. For this, we are going to the source. So write and read data width will be the difference. So we are going to read 32 bits of the data. We are going to write 8 bit of the data, but we are going to read the 32 bits of the data at the one called cycles. Okay, so here for this, let's suppose we are going to the left. I was just writing to the 32 space. Okay, guys, so here right data bus is 8 bit and the data bus is 32. That's first to answer. And here, yeah, 32 bit. Okay, guys, so now we are going to regenerate because this will be again, it is going to be resynthesized. We synthesize that fiber. Okay, so for a few moments we'll be waiting and it will be resynthesizing all the. It's going to create the new DCP file as we saw here, right in the IP source. There was a DCP file. This DCP file is going to be recreate. Okay, and this session file will also be recreated. Of the buses. And we're going to make it, we're going to change slightly now. We still code for the read bus. All the parts will be remain same. Till now, I'm going to post this video so that it will get numbers. So guys, now the DCP file has been created as you can see here, and the Fifo generated.vsu and video. Both the top file has been also regenerated, and so I'm going to go here. You can see the reload. So here you can see the top file, and it is now 32 bits. So input will be the same, and output is different. I'm going to copy this. Okay, so I'm just going to paste over here. I'm just going to write this. I just override it, and another my output will be the 31.0. Okay, and 31.0. So this everything's fine. So I'm going to save it, and I'm going to relaunch the simulation. So I'm going to relaunch the simulation. We're waiting for some moment for that asymmetric hyper implementation. Okay guys, now you can see here that the output port is 32 bits. Now I'm going to give the clock. I'm going to force clock 01 and clock is 10 nanosecond. This is signal I'm going to high with high and write name on the 0. This is 0. Okay, I'm going to wait for some clock cycles. Okay guys. Okay, now I'm going to put some data on the Fifo. Yes, I'm going to put same data one. I'm going to make the receipt as a low. Receipt as a low and write the data as high. Okay, so now I'm going to write the data converted to cycles and data I'm going to write the 5 other data I'm going to write the 6. Okay. Here now full flag is low at and empty was high, right? For the 4 clock cycles, because we're going to read the chunk of the data and the 1 clock cycle. So if I make the right neighbor as a 0 and let me make the read neighbor as a 4. Okay. So we are going to read the data. Now you can see in the data bus we are reading to the data. Okay, so let me make. So here all the data is concatenated that we earlier is we write over here. Yes, here you can see. As you can see, we write the 1. It is not considered because the reset was high. After reset is low, this all the data is 1, 2, 3, 4 bytes of the data has been written. That's why you are seeing here is in the reference 02, 03, 04, and 05. And the 06, once we have right, let me make it as read enable and the light enable is high. And we are going to write the chunks of data. Returns as 7. And I'm going to write it as 8. And read enable is again high, but then again we are not getting the data on the data bus. But after the 4 clock cycles, only we get the data 06, 06, 06, and 07, right? Until the 4 byte has been written, we will not get the data on the read bus. Okay, because we are reading the 32 bit of the data and the one cycles. Okay, guys. So in this way, you can do the Fifo, asymmetric Fifo. Okay, guys. So thank you so much for connecting with me, and please do like and subscribe my channel for the incoming videos at PGA Techno at PGA series. I'll be demonstrating lots of technique. And I'll be presenting I'll be presenting and I'm creating some PPT as well so that I'll be presenting on incoming videos. Okay guys, thank you so much for watching.